Well, welcome everyone. Welcome to the Gruber Prize Ceremony and Lecture. I'm Deborah Elmgreen, President of the IAU. I'm delighted to celebrate the 2024 Gruber Cosmology Prize winner, Dr. Marcia Rieke, as well as the Gruber Postdoctoral Fellowship winners. The IAU has enjoyed collaborating with the Gruber Foundation since 2001, since we share the common goal of striving for a better world through science. With these awards today, we honor breakthrough science from a generational leader, as well as the promise of great advances from the next generation. For our ceremony, I'm pleased to have with us Executive Director Marcia Rieke from the Gruber Foundation, as well as past Gruber Prize winner Richard Ellis, and IAU President-elect Willie Benz. So without further ado, congratulations to all our honorees, and I'll welcome Sarah to the stage. Thank you.
Good afternoon. Welcome to the presentation of the 25th Annual Gruber Cosmology Prize, honoring a leading cosmologist, astronomer, astrophysicist, or scientific philosopher for theoretical, analytical, or conceptual discoveries leading to fundamental advances in our understanding of the universe. On behalf of all of us at the Foundation, we are pleased to be here in Cape Town to present the prize at the 32nd General Assembly of the International Astronomical Union. And thank you, Deborah Elmgreen, for your warm welcome. The Cosmology Prize is presented annually in conjunction with the International Astronomical Union, whose support and partnership has guided our efforts since the earliest days. It is my pleasure to introduce Willie Benz, President-elect of the IAU, who will say a few words about our fruitful collaboration.
Good afternoon, everyone. As was said by our president, the IAU is very pleased to have collaborated with the Gruber Foundation since the prize's inception. In this business, the IAU has an advisory role in the constitution of the Selection Advisory Board for the prize. As part of our collaboration, we are fortunate as well to receive an annual grant of $75,000 US to be awarded to postdoctoral fellows around the world so they may pursue education and research at a center of excellence in their field. Over the years, the fellowships have been awarded to young scientists from Algeria, Chile, Poland, Taiwan, India, Spain, Italy, Israel, Greece, Belgium, the Netherlands, the Russian Federation, Mexico, the UK, Colombia, Egypt, Ecuador, and the United States. So as you see, it is a global enterprise here. We usually receive between 30 to 50 outstanding applications, which, as usual, makes the selection process difficult. And this year, I must say, was no exception. Nevertheless, we managed, the selection committee, to come to a consensus and decided to award the fellowship money to 3 winners. And the winners are, but you know the name already, of course, Aldana Grishner, Jonathan Alexander Quirola Vasquez, and Honghui Liu. Congratulations to all 3 of you. Now let me just say a few words about these 3 outstanding researchers. Adriana will investigate the electromagnetic weak and gravitational signatures from the formation of the heaviest element in the universe and assess the contribution of massive stars and binary to our process enrichment across cosmic time. Jonathan Alexander will focus on unraveling a new type of transient population, the fast X-ray transient detected by Chandra, XMM Newton, and Swift XRT. To determine their nature and cosmic rates, he will identify their host galaxy and track their contemporaneous counterparts. Honghui Liu will study accreting compact objects with X-ray observations. He will use the constraints given by polarimetric and spectroscopic measurements to derive the best coronal geometry. He plans to apply his model to archival data from simultaneous XIPE, New Star, Insight X, HXMT observation of X-ray binaries. Now, in addition to the fellowship, our winner will also receive a certificate from the IAU recognizing their achievement. And I have them here. So maybe we can, if we have the winners online, and here they are. Hello to the three of you. I'll show you your certificate. Here they are, the three of them. So that is the three certificates. So while I have you on screen, I would like to really congratulate you again for being such outstanding representative of the new generation of astronomers taking over from us, slowly but surely. I wish you all the best in your scientific career, and I would like everybody to give them a round of applause. So that completes that part of the ceremony. Thank you.
Thank you, Dr. Benz, and congratulations to Aldana Greichner, Jonathan Alexander Quiroga Vasquez, and Honghui Liu. It was fun to have them on screen. It would have been nice to have them in person. Moving on, the Gruber International Prize Program, established in 2000, recognizes achievements and discoveries that produce fundamental shifts in human knowledge and culture. While we are here to honor the achievements of Marcia Rieke, let me mention that the 2024 Genetics Prize was presented at the Allied Genetics Conference on March 10th to Hugo Bellin. On October 6th, at the annual meeting of the Society for Neuroscience, the Neuroscience Prize will be presented to Corey Bargman and Jerry Rubin. Please note that nominations to the 2025 Gruber Prizes will be open until December 15th, and that we encourage nominations that reflect the breadth of the fields and the diversity of those working within them. Before we return to cosmology, I would like to acknowledge our co-founders, Peter and Patricia Gruber, whose combined vision and leadership established our International Prize Program, and whose care in doing so gave it the legs to stand on its own. Peter has passed, but Pat remains the heart of the program and is a lifetime member of the board of directors. Returning to cosmology, we are proud of our illustrious laureate roster, and we are so pleased to be adding to it today. The 2024 prize recipient was chosen by a distinguished selection advisory board. We deeply appreciate the knowledge, commitment, and enthusiasm that these advisors bring to the judging process. We could not do this without them. Let me now invite our 2023 prize laureate, Richard Ellis, to present the official citation to this year's prize and introduce the scientific accomplishments of our recipient.
Good afternoon. It's a privilege to read this citation. The Gruber Foundation is pleased to present the 2024 Cosmology Prize to Marcia Rieke for her pioneering work on astronomical instrumentation to reveal the breadth and details of the infrared universe. Her contributions to flagship space missions have opened new avenues for understanding the history and mechanisms of star and galaxy formation. She enabled the development and delivery of premier instruments providing groundbreaking sensitivity to near-infrared wavelengths to both the James Webb Space Telescope, particularly NIRCam as principal investigator, and the Hubble Space Telescope, Nick Moss as deputy PI. Through these substantive contributions, along with her earlier work, Marcia Rieke has had a lasting impact on our understanding of the universe. Now, if I could add some personal remarks, just to embellish this very nice citation. I first met Marcia in 1978 at the Objects of High Redshift conference at UCLA. And for the younger people in the audience, the highest redshift object in 1978 was a cluster of galaxies at a redshift of 0.56. So that places the progress that we've been hearing about at this meeting into perspective. In the early 1980s, infrared arrays began to emerge from declassified military programs. And Marcia was a pioneer in exploiting and developing these early cameras. If it can be imagined, these early cameras were 30 by 30 pixels or so. And while they were small, they were considered a revolution at the time. And I remember myself using one of these cameras and realizing this was the birth of a revolution in infrared astronomy. That revolution has been championed by Marcia and her colleagues, particularly in space. These early cameras fueled the idea of the Spitzer Space Telescope, where she was also involved in the MIPS instrument as a co-I. But eventually, of course, the Hubble Space Telescope, largely up until that time an optical and UV telescope, had to have one of these new detectors. And of course, that led to Nick Moss, where she was the deputy principal investigator. I was on the original panel, the Dressler panel, HST and beyond, which proposed the idea of a next-generation space telescope. After that report, the James Webb Space Telescope was, of course, developed. But the concepts were very early in the 1990s. Marcia chaired the science working group at a critical stage in the development of James Webb. And as a reward for that, she was awarded the principal investigatorship of NIRCam, one of the premier instruments, of course, on James Webb. Now, progress in observational astronomy, in my view, is driven by two things. One, scientific vision and determination. And secondly, technical progress and expertise. And Marcia is that rare individual who excels at both. And innumerable astronomers, particularly many hundreds of them here, have benefited from her work as a result. So Marcia, I invite you to come up and receive the Gruber Prize for 2024.
I thank all of you for coming this afternoon, and I especially thank the Gruber Foundation for this wonderful award. When we were first starting to work on JWST, we thought that, it was supposed to launch in 2009, and it was going to be, something amazing and all that. But instead, it took several decades, but we got there. And at the end of that, my real reward initially was just it worked. There's data for my postdocs. I don't have to worry about having wrecked their careers by making them work on this instrument for N years with no data. And so I am just stunned that I got this award, because I never thought of any reward beyond getting data that propelled us forward. So I was just amazed. So let me talk a bit about how we got to a launch in late 2021. It was Christmas morning, 5 a.m. in the US, and why I might have started along this path in the first place. So part of the story starts way before the idea of having the JWST mission. And there was a reason why the infrared spectrum was attractive for studying distant galaxies. And I will try to highlight some of that as I go along. Before I get too far into the talk, I want to thank numerous collaborators. The right-hand picture here, whoops, there we go. This is what we called the wooden JWST, a life-size model that Northrop Grumman made, and it visited a number of places. And this was the crowd of people working on the project already in 2005. And ultimately, over 10,000 people worked on this to make it happen. But I want to especially recognize this other collaborator. Please stand up, George, because many of the key things many of the key ideas that made NIRCam so successful, and also many of the steps along the way, were because of our collaboration. And talk about someone who supports you in your career. When your husband stays up late thinking about how to design your instrument, can't ask for anything more. Okay, and of course, one of the ironies for me of JWST is that you notice that George is the sort of the MIRI co-PI, and I originally joined the JWST project, the Ad Hoc Science Working Group, to promote the existence of MIRI, and ended up being the NIRCam person. So that's how it goes. All right. So when I first started working on high redshift galaxies, the goal for what we were trying to do was very different from what is going on with high redshift galaxies now. And with Hubble, he established that redshift is a distance indicator, and that then led on to many other things, including the development of what we called the Hubble diagram, which was a plot of apparent magnitude versus redshift in curious units, depending on how they did things in those days. And you will notice some curves superposed here with this strange parameter Q0 that we no longer use. It was called the deceleration parameter, and it was a stand-in for the total mass in the universe. And the idea was that by measuring how the brightness of a standard candle changed with distance, you could determine how much mass there was in the universe, because of the mass changed the light path. And so people had established more or less that bright elliptical galaxies in clusters were standard candles, and so you could measure the brightness of those as a function of redshift, and you could map out whether or not the universe had enough matter to be a closed universe or a flat universe, or would expand forever. So that was the initial game, and because it depended on measuring a brightness accurately as a function of distance, it was clear that because of the shape of the spectrum of an elliptical galaxy, the near-infrared would be a good place to pursue this initially, because the redshift would be moving into the infrared band, the visible portion of the spectrum, and we knew that very well. Whereas the visible portion that was getting measured, it was sampling the ultraviolet, which was not so well known. So the idea was it'd be more accurate to do this in the infrared. And let me just give a little presaging of where we would end up later. So if we look at the Hubble diagram for a cluster of stars, at a young age, that's a kind of age similar to what we're now measuring with JWST, and we look at the main sequence turnoff is quite hot, but there are already giant branch stars that have, or supergiant stars that have evolved from here. And if we compare where the tip of the main sequence is and where the giant branch is, with later times, you can see that it evolves down, and now we get down close to where we are today. But you notice that the giant branch color doesn't change much, but the luminosity changes by nearly a factor of 1,000. And so when we were playing this game of trying to map out the shape of the universe by assuming that galaxies were standard candles, we were fooling ourselves, because the luminosity of galaxies changes so quickly that once people realized this, there was no point in this Hubble diagram game. And we switched instead to thinking about how to measure evolution of galaxies. But let me give just a little overview of what it was like to measure galaxies at redshift of 1/2 to 1 in the late 1970s, early 1980s, before infrared arrays. So up here, you can see a picture from a paper by Rich Krohn, High Spin Rad, and others. And this object in the upper blue circle is a galaxy at redshift of 0.95. This was one of the record holders for a little while. And you can see it doesn't look like much. Down here is a Palomar sky survey plate, something that people have almost forgotten about now, but we used it for making finder charts. And so the idea was that if you were a near-infrared astronomer, you could measure this stuff if you did the following. You have a nice photometer, the detector's on the back, and this front eyepiece was what you could look through to get things lined up. And George had cleverly figured out a way so that, infrared astronomers always were given bright time because the OH airglow from the night sky is brighter than the full moon. So give us the full moon time because it doesn't bother us, but it does bother us in that you can't see anything to find, point at. So what George had devised was a photometer that included these, they look like just little handles, but they each ran a very precise screw that one full turn moved this eyepiece a millimeter. So if you measured the plate scale accurately, you could line up on a bright star, calculate the distance from that bright star to your object, turn the screws the right number of times, and that would and move the telescope to keep the guide star centered, and you could point at something faint. So you would initially point at this, start turning the screws, and the telescope would end up pointing at this galaxy shown here. That's how we made the following kind of plots. So we measured the near-infrared color, and this is the no evolution track, and you can see that some of the data were a little scruffy, but it was hard work. And then over here is a 2-micron or K-band Hubble diagram, and even this data set made it clear that the galaxies must be evolving and getting more luminous. And so by combining the fact that there's no color evolution and what we were seeing here. And then all of this definitely got propelled into a different direction because of the discovery of dark matter and so on. And that just rendered this whole point of trying to measure the shape of the universe from assuming standard candles just moot. It was a silly idea because obviously stars evolve and galaxies are made of stars, and so galaxies evolve. And this was before we even thought of all the complications of merging, et cetera, et cetera, et cetera. So Richard has already alluded to the history of JWST, and the HST and Beyond report came out here in 1996. That's what triggered NASA to actually start allocating real funds, not just sort of people studying things a little bit. And there had been various notions early on, but it wasn't until the early 90s that people could see that galaxies were likely to be compact enough and therefore not so spread out that they couldn't be measured. And by the time the Hubble Deep Field was imaged, it became clear that we weren't going to run out of a galaxy population. We were running out of the ability to measure them. And so we needed something else, which of course the arguments were well summarized in this report. And then JWST, but then called Northrop Grumman, not Northrop Grumman. There are people that said it was called Next Generation Space Telescope, had to be changed because the company was Northrop Grumman Space Technology, so it sounded the same. And you can see along the top row some of the progress in detectors. So let me just make a minor comment, or not so minor comment, about why it's important to go to space to do infrared work. I've already alluded to the fact that on the ground, the OH airglow is brighter than the full moon, which means that even in the near infrared, it's like trying to see a tiny faint thing against a very bright background. And if you go to the Miri wavelengths, it's even worse. So this guy is holding a match. But if you get rid of the background, it's so much easier to see. And that's the whole reason to go to space, is to get rid of that background. It also helps that there are some parts of the Earth's atmosphere that aren't very transparent at infrared wavelengths. So, precipitated by this HST and Beyond report, aerospace companies started thinking about what format there should be for something like JWST, and you can see some of the early concepts here, no one of which is exactly like what actually got launched. There was a lot of work to go, and there was a lot of technical development that was required to get at that time, 8-meter telescope down to a mass that an existing rocket could lift. One of the early D-scopes was to go from 8 meters to 6.5, and then the size stayed the same after that. So, and of course, along with this developing technology and things, another thing that was beginning to be understood, partly as a result of the Hubble Deep Field and work by Chuck Steidel and others with the idea of Lyman dropout galaxies, galaxies that where their ultraviolet radiation was all absorbed by the intergalactic medium. And so it became obvious that Hubble just wasn't going to do it. And I'll give you a little intro to that here. So here's the output of a galaxy at redshift of 3. And Hubble filters do a very nice job of outlining the output of that galaxy. And you can see that, JWST, of course, can do a lot on it as well. Now, if you move to Z of 7, you can see that this edge, very sharp edge, caused by absorption in the intergalactic medium, is wiping out the output of the galaxy. And at this point, at this redshift, HST still has some filters. But as we go to the last step in this little sequence, by Z of 10, you can see that the limit of HST is being reached. And some of the early detections, like GNZ11, that was the highest redshift object that HST ever detected, was basically detected by HST in only one filter. So you had to have some confidence that that one filter was showing you what you thought, and that wasn't some other extinction or a bright emission line or something conspiring to make you think it was distant. So it was by 1996 very clear that we needed a large cold infrared telescope in space if we wanted to go any further. And along in this same time frame, thank goodness, infrared detectors went right into a realm that would warrant being launched on a big, expensive mission. I mean, I remember when George and I got our first 32 by 32 array, a whole kilopixel. Can you imagine selling a digital camera with a kilopixel? No one would buy it. Well, anyway, we thought we'd died and gone to heaven. It was just fantastic. And as time went by, and partly as a result of the NICMOS project, we got larger and larger arrays, and Spitzer also helped propel the array development quite a bit. So by the time we were really serious about starting the JWST, we were getting into the kinds of arrays, and these are pictures of actual flight arrays, that warranted being launched into space and have provided the wonderful data that we have so far. And as George is fond of pointing out, we do better than, infrared detector arrays were doing better than Moore's Law for quite a while. So it's pretty clear that the idea for JWST was to penetrate as far back into here as we could get. And when I made this slide a while ago, I said, well, maybe you can get to Z of 15. We're at Z of 14.3 and counting. Stay tuned. I'm sure we'll find some more. And while JWST was being constructed, Spitzer was launched in 2003, and Spitzer provided a number of impetuses that really pushed the high redshift galaxy game further. And here, for example, are a couple of galaxies where the Balmer jump, which indicated relatively old stars, were being found at a redshift of 6 and 7. And again, no one had predicted that. But if you look at this plot of, here's several different galaxies, all from Z of 9 to 10, and you can see, the HST data, you can barely see these little dots. And unfortunately, Spitzer, they don't look very impressive because Spitzer's primary mirror, although it was very cold and could make very sensitive measurements, was smaller than one segment of JWST, which meant that the angular resolution was not very good. But this just whetted people's appetite. And another thing that was quite intriguing was that by making a lot of measurements with the IRAC instruments at 3.6 and 4.5 microns, and these two filters actually have very close analogs in NIRCam, you could see that there was some, for particular redshifts, there was a shift in this color that implied that something funny was happening, and that something funny was a strong H-alpha emission line in one of the filters. And we should have realized then that slitless spectroscopy on JWST was going to be a powerful tool because Mother Nature was providing us with extremely strong emission lines that would show up well in that kind of observation. And so now we get to where we're actually, we've gotten into the design of NIRCam, and you can see that it has two identical modules that point at adjacent pieces of the sky. And the reason that we designed it this way was that George and I reasoned that if we had the two identical modules, because NIRCam is the tool used to keep the 18 mirror segments co-aligned to act like a single smooth telescope mirror, if we had two identical, then in NASA's, this would be called fully redundant. And if something broke in one part of NIRCam, there was still the other part that could do this wavefront sensing. I have to say, as an aside, learning about all of the wavefront sensing, I really went past thin lens 1 in the optics regime. There was a lot to learn there, but NIRCam was equipped with the right parts to do that. And from the science point of view, having these two identical modules meant that we got to survey twice the area at once, which is very helpful for looking for high redshift galaxies and doing surveys. And you notice that there's a blue and red outline. The red outline is the footprint of a long wavelength array on the sky, and the blue are the 4 short waves. So not only do we have 2 patches of sky being measured, but we have 2 wavelengths being measured. And we equipped NIRCam with a nice suite of filters which have proven to be very effective at measuring photometric redshifts, which of course are aided and abetted by the fact that this problem for HST, that the intergalactic medium absorbs all the light below the Lyman limit, that makes a very good redshift indicator. We also were interested in combining imaging with spectroscopy, and NIRSpec has, for the first time, provided multi-object spectroscopy in space. And you can open and close its shutters. This was a real trauma to get this to launch, because we discovered in one of the tests that vibration testing tended to break some of the shutters, and some of this had to be redone. Not fun late in the game. But they can be electrically closed and opened, so you could program what you were pointing at. But the one thing that was a little bit tricky is that for a ground-based multi-object spectrometer, you use a probe that you typically can move, or a plate that you drill holes specifically for your objects, and then you change the plate. Here, where the slits were was fixed on a rigid rectangular grid. And all you could do was open and close them, which meant that sometimes you had to make some compromises. And so first you had to measure some reference stars. This happens autonomously in space. It points, and where the reference stars are located is known. And what this does is JWST can rotate around a little bit. An exact precise angle is not quite good enough for pre-programmed opening of the slits. So you would have picked out the slits, and you would measure these reference stars, and then you could tweak up the rotation a little bit. And you will see that there are some, like this target here is right on the boundary between 2 shutters, and then there are other ones that are shown highlighted in green here that were good. And so when you plan an observation to get lots of high redshift spectra at once, you have to do quite a bit of work to figure out exactly which slits to open and things, and that's quite a bit of work. On the other hand, it's a whole lot better than having to measure one source at a time when it takes 100,000 seconds to get a good spectrum. And another thing that has complicated use of NIRSpec is just the laws of physics. So on the top here is 1.4 microns down to 4 microns. That's not even the full range of the instrument, but you can see that diffraction changes by just the ratio of the wavelengths. And so that makes calibrating the spectra some work. And one of the best things we found to do is to take the NIRCam image and project the slit pattern onto the image, and then you can figure out what fraction of the light is actually getting through the slit at each wavelength. And another thing that is tricky is that this is the number of spectra you might like to get, and this is the number of targets in the field of view. And if you don't have enough targets, you won't get to the optimum number of spectra possible, because there are too many that fall, on the cracks between the slits and things. So you need a high density of targets, but that's okay. Deep surveys for distant galaxies have lots of targets. And let me not forget MIRI. I will show some data. MIRI has proven to be more powerful at redshift 14 than any of us would have ever guessed. And in particular, more powerful than some of the NASA administrators at the time we were selecting instruments. And I'm so glad that I was persuasive enough, along with a few other people like Aveen Van Dieschuk, who was my co-collaborator in trying to get MIRI on this mission, that we succeeded. And it's, we haven't yet done some of the observations that I used to promote it, but it's very clear, since it's now the most requested instrument in proposals, that the mission would not be the same without it. So we've gotten to the point where we've actually built hardware. We did a test of the instruments cold and attached them to the telescope at NASA Goddard Space Flight Summer in the summer of 2017. And then it was moved by aircraft to Houston Space Flight Center, and in Johnson Space Flight Center in Houston. We had the misfortune of being there when Hurricane Harvey hit. That was an exercise in and of itself, but the test was successful and kept going in spite of almost running out of liquid nitrogen. And then the last bit of construction happened at Northrop Grumman, went by boat through the Panama Canal, and ended up at the Ariane Space Launch Site in French Guiana. And this just shows going into the airplane, and that portable clean room that holds the telescope and instruments has only about 2 centimeters of clearance with this airplane. So the guy driving the truck was very skillful. And as it turns out, we had the same truck driver from here at Johnson loading it onto the airplane, all the way through loading it on the boats and stuff and taking it off the boat in French Guiana. So he was a very good driver. This shows the test chamber at Johnson Space Center, and you can see from the size of the people, this is huge. It was built to test the lunar rover, and the project had to do a lot of work to clean it up. It was not intended for precision optics to go inside. And you can see here's what it looked like. This purple stuff here is extra radiators used to get the temperature down to match what we thought we would have in space. And there was some test optics up here. Then when we got to Northrop Grumman, we got connected to the spacecraft and the sun shield. And here are the cables and things that go up to mate to the cables coming down from the instruments. And I'm very glad I was not the person that had to connect these. So we finally made it to late 2021. There is the launch on Ariane 5. And this unfolding sequence that I don't know how many of you ever saw the video of the unfolding, but when you would show that at a colloquium or whatever, there were a lot of astronomers that looked at me and said, "Are you nuts? Why are you spending so many years of your life? And that unfolding's never going to happen." And I would go to meetings in Washington, D.C., and there was a person who shall remain nameless, but he was a former CEO of Lockheed, and every time he saw me, he asked, "Do you really think that's going to work?" Well, the answer was yes, I did, and I'm glad I took the chance. But as you can see from the head of NASA Space Science at the time, you know, it was scary, and we were so relieved when we were relieved that the rocket worked right. We were relieved that everything unfolded right, because by the time we got down to here, fully unfolded, most of the things that could go wrong were behind us. So let me just talk a little bit about the launch. Here's the launch site in French Guiana. And also, I want to point out that this project is an international partnership, and there are 17 different countries that contributed to getting the equipment built. And it just shows what can be done when you have a diverse set of people working toward a unified goal. And if you, later in the meeting, you want to ask George about what it was like to get MIRI built as a collaboration between Jet Propulsion Laboratory and Royal Observatory Edinburgh, with all kinds of people from NASA, et cetera, in the middle, he can tell you that it was very important to have a completely unified front by the scientists. And he and Gillian Wright, who is his counterpart from the UK, were very good at making certain that they could clearly say what they were going to do, and that fended off some of the issues. And I also want to point out this picture that I got from NASA. You'll see that there are two pins that don't match. NASA forgot two pins. One pin is for the tracking station in Canberra, because JWST generates so much data that there are several downlinks a day, and there are 3 ground stations, one of which is in Australia. And then you notice there's a pin on Africa. And the European Space Agency has a tracking station at the little coastal town of Malindi in Kenya. And that tracking station, we launched from here, and we went off into space across here. And this tracking station was positioned perfectly to measure exactly what the trajectory imparted by the launch was, which meant that we could calculate how to do the first course corrections for getting to L2. And so this African tracking station played a role in making certain that JWST has this 20-plus year lifetime because of the tracking that was available from there. So we got through space, we got through 6 months of commissioning, we got all the mirror segments aligned. This is when I finally did my, everything's okay moment. And this is a lovely diffraction-limited, actually better than diffraction-limited image. The combination of the mirror and NIRCam are diffraction-limited down to 1 micron, which is quite a bit better than projected. And if you have sharp eyes, you may notice a few little blobs in the background. Those blobs are all galaxies, and this is when it hit me that this telescope that we had designed to detect galaxies, in fact, was detecting them all over the place. And there are some of the early release images of planetary nebulae that, I looked at first and I said, oh, it looks like, how's there a scratch in that picture? It was an edge-on galaxy. And so we say that galaxies like to photobomb pictures. And this just gives another graphic view of, here's a Hubble Deep Field image. You can see the spiral here and how much clearer it is with JWST. We had not expected to exceed the image quality of HST, but that's partly why many things are working better than we had thought, is the image quality is superb. Now, the other thing that, of course, matters is moving into the infrared. And so this is one of the early release fields, and it's blinking between HST and JWST. And the HST one has a slight greenish cast. And for those who are sitting close enough in the front, for example, there are objects like this one that only show up in the JWST image. The universe has shown us that there are many red galaxies, partly red because of redshift, partly red because of what groups of stars they have. Some are red because they've got a lot more dust than we would have guessed ahead of time. And so this increasing the spectral range that's available with this kind of spatial resolution is just, that's partly why we have to have whole sessions here dedicated to JWST results. And so that then brings me to the science that my team and I have done with this JWST Advanced Deep Extragalactic Survey, which is a collaboration between 3 instrument teams. And it's been fun getting everyone together on the same page, but it actually wasn't that hard. And the team has grown to be over 100 people now, most of whom are young postdocs and grad students. And we've divided up various parts of the science program, and different people are doing different things, but there's plenty of data to go around. And so the idea of the JADES program initially was to take deep images with NIRCam, use the technique of photometric redshifts to figure out what are likely to be distant galaxy candidates that we would want to take spectra of, and then you can see these little yellow slits here point NIRSpec at what we think are the likely distant galaxy candidates. Because unfortunately, as powerful as NIRSpec is, we can't, at the moment, at least with the amount of time we had as instrument teams, get spectra of everything. That doesn't work for us. We had to be choosy. And this is just an example of how well the photometric redshifts have worked. And yes, there are a few outliers here, but in the very highest redshift regime that you see over here, the IgM absorption causing the dropout shortward of the Lyman limit makes the redshifts pretty accurate and not so many dropouts. If you asked me to give you a sample of high precision kind of Z of 2 galaxies, that's a little bit harder. So we got our first sets of data in late September 2022. We analyzed them very quickly, and it turns out we had practiced, since there was a 2-year launch delay, we ended up being able to practice on synthetic data the whole process of analyzing, measuring a photometric redshift, and then transferring that information to the slit selection team. And so when we got the real data, we were ready to go quickly. And so you can see here how the short wavelengths are blotted out by the intergalactic medium, and there are in blue the data from NIRCam, and the red is a modeled spectrum fit to the points that's used to estimate the photometric redshift. So these were 4 that we picked out, and we were so happy that one of them was Z of 13, which we had not initially expected to find so quickly. And this just shows, here are the actual images. This happens to be the Z of 12.6 object. And you can see how there's nothing in the centers of the shortest wavelengths. And when you get to the longer wavelengths, you see it more easily. This just shows it graphically. And by luck, we were able to get those 4 in our first batch of spectroscopy. The original plan was that we'd get some imaging, and it would take a couple of months, we thought, to process it. And the end of the visibility period for good south meant that we probably would not be able to get spectra of objects selected from the first imaging. And so the first spectroscopic run was set up to target distant objects from Hubble Space Telescope data, because there were some interesting ones there. What happened was that NIRSpec has a little quirk that every once in a while it gets what's called an optical short. So one of the things that operates, one of the circuits operating a shutter starts glowing, and they have to go through a little procedure to clear it. And that happened just before our first spectroscopic run. And it was then going to be about 2 weeks before our data could be rescheduled. And so we needled Peter Jakobsen, who is our guru of slit positioning, and said, "What do you think, Peter? There are these four galaxies that fit in the pointings we already have. Can we sneak those coordinates in?" And he said, "Oh, no problem, because I have to go check everything, because 2 weeks from now, the position angle will be slightly different, blah, blah, blah. So we're going to have to change things a little bit anyway." So he got them in, and so we got these four objects, got the spectrum measured right away, relatively speaking, and we were ecstatic because our selection procedure had worked, and it had worked beautifully. And ironically, although in my mind, these dropouts were quite obvious, particularly in the 2D spectra down here, the referee said, "I won't believe this unless you get emission lines." Well, this is an object at Z of 9.4, a little bit lower than our 4 prime objects. And you notice over here, you can see 3 strong emission lines, 2 from 5007 and 1 from H beta. When you get to Z of 10, these fall off the end of the near spec sensitivity range. The detector no longer works out that far. And this is a very, quite a bright object, so you can see some other faint emission lines, which with the quality of data we had on our first high redshift ones, you could not see. So this was kind of, we didn't have this spectrum at the time that we had to answer the referee, but we danced around and he finally agreed to let us publish the paper. And this is just an improved version of that original highest redshift guy, because we got some more data later. And you can just see the outlines of the slits, and there it is in the slits. And so this redshift of 13.16 means that the light that we were detecting in this spectrum was emitted 327 mega years after the Big Bang. And that was just, we just could hardly believe that we had done this. And so at this point, we could say we've succeeded at the big goal. We said that we would take images, we'd get spectra, we'd find the most distant galaxies. But of course, whenever you have a record, it's meant to be broken, and I don't know exactly how long this record will last, but not forever. And so we have 2 more candidates that we found in some of our subsequent imaging and in a later round of spectroscopy. And one guy is at 14.32, and the other is at 13.9. And something that's very intriguing in the 13.9 is that it looks like we might even be seeing carbon in that galaxy at 13.9. And so I think we're, and I'll show some more evidence in a moment, we are challenging our ideas of how elements get formed in the very early universe. And one thing that's helped with this whole process, but it's also a puzzle that's challenging the theoreticians, is that many of these early detections, as shown on this age of the universe plot versus absolute magnitude, these galaxies are quite bright. And we're seeing this over and over and over, and there are various theories about, is star formation efficiency higher? There was an early debate about whether lambda CDM was broken, and we got rid of that fairly quickly, but nonetheless, there is something different about the star formation at these highest redshifts that we simply don't understand right now. And if you go and look at the poster session associated with the JWST symposium here, you find this coming up over and over. And I'll mention GNZ11, which Richard also mentioned in his introduction. And here is a nice spectrum. And when I first showed this to some of my colleagues at Steward in Arizona, they could not believe that this was at redshift 10.6, because you're seeing all kinds of metal lines that this was beyond our wildest dreams, let's just put it that way. But it helps that this object is indeed very luminous. And the existence of a nitrogen-4 emission line has prompted a discussion of how much light from this object is generated by an AGN or a black hole at its center, and that debate is ongoing. Now we turn to what MIRI has done for the high redshift universe, something that, again, our friends at NASA headquarters would not have predicted, because they said, we're going to run out of dust. You don't need to have a mid-infrared instrument if you're looking at the high redshift universe. What they forgot was that at the highest redshifts, MIRI gets to see our friendly old 5007 oxygen and H alpha. And this is being observed at redshift of 12.4. Amazing. I mean, this was a project that I would, even in my optimistic days on the old ad hoc science working group, I never would have proposed this as a way to justify MIRI. But here we are. It's showing how useful the mid-infrared is even at these high redshifts, and that's partly because the universe is cooperating. Things are brighter than we expected, and MIRI is going to be contributing much more in this arena, I'm very certain, because not only can it extend the range over which we can see our friendly rest frame optical emission lines, but we may be able to look for higher redshift Balmer breaks and so on to see just when the cool stars have started showing up. And we may also learn more about element enrichment. Not to be forgotten is that the spatial resolution of JWST is good enough that we actually can discern shapes, and there are parts of various teams busy working on understanding the morphologies of these high redshift objects. And we also have the ability to use medium band filters in NIRCam to isolate some emission lines. So this is the broadband image, and then here is a medium band image where you can see evidence of an outflow. And this picture reproduced under this plot that I can't get rid of shows a lot of extended emission, most likely from H alpha around in here. And just what's going on with these extended emission line structures is, again, something we need to ferret out. Let me finish with a couple of special kinds of galaxies. This object, where it has very strong Balmer absorption lines, but yet is basically like an elliptical galaxy. We used to, in the old days, call these E+A galaxies. They're now called quiescent galaxies. And what's remarkable about this one, aside from the fact that it's at Z of 4.7, is that it has broad H alpha. And that's not something that's seen in these so-called quench galaxies in the local universe, or seen rarely. And not to be outdone, we have also a galaxy showing these strong signatures of an A-star population up at Z of 7.3. And again, we had not planned on finding galaxies like this at these redshifts. And last but not least is a paper that Joris Wittstock and Irene Chevalier led on some spectra of a galaxy at Z of 6.7, and you notice there's a little dip here, so this is the continuum of the galaxy, and you can see it magnified up here. This is the 2100 angstrom carbon absorption feature, dust absorption feature, seen at this redshift. And to make that kind of absorption feature requires a lot of carbon. And this plot shows this dashed line is, the limit at which you could presumably even see much carbon at these redshifts. And so, again, something different is happening with this star formation to get these kinds of abundances of heavier elements so early on. A little advertisement for those of you in the audience who want to go play with some data yourselves. We have released a lot of our data now and spectra as well, and you go to this site at Space Telescope Science Institute, and you can download mosaics, catalogs, spectra, and find things that we've missed, and I'm sure there are a lot of those. So let me just conclude by saying the best is really yet to come. We're only a couple of years into this mission, and many puzzles are being presented, and now with subsequent calls for proposals, people are going to be able to tune up their proposals and figure out what is causing these things that are happening at high redshift that we, at the moment, can't quite figure out. And I'll mention there are a couple of talks, plenary talks tomorrow. One from Richard here on the progress he's seen. And of course, ongoing all through today are talks in this IAU Symposium 391 at the West Ballroom down the hall. Thank you.
Marcia, thanks for sharing your remarkable behind-the-scenes story with us. How inspiring. We have time for some questions. Marcia, what I've admired about you for so many years is just all the remarkable development, just the forethought that went into these instruments. And I know you've shared with me a bit in the past, maybe the audience would like to hear, how did you start on this journey?
Oh, I started on this journey, I decided I wanted to be an infrared astronomer because I wanted to do something new and different. And when I was a grad student, infrared was, literally way out there. And when I was a grad student, I kept reading about these guys in Arizona that would kept opening up new wave bands and stuff. I said, that's for me. And so then George advertised for a postdoc. And thank heavens I got the job. And he had already been into measuring at that time, really nearby galaxies in the infrared, but again, it was hard work because you couldn't see them very well, and he'd worked out all these ways to pointing at something you couldn't see. And he got me really sucked into the galaxy game, and then when it came time for me to start thinking about, how do I want to make my own mark? And it was a time when there was a lot of ferment in finding distant galaxies, and we're trying to measure the shape of the universe, bad idea, but you could see that the trends for measuring evolution of galaxies were coming up, and it just seemed like the thing to do.
And we're all glad for that. Yes. Sarah. Wait, no, she's coming. She's running.
Running, but no tripping, please.
Thank you for this incredible inspiration from your talk and your work and your life. I'm just wondering, so of all of this amazing result, what's your favorite gem of your career and the results that you've seen?
If I look back over my whole career, there are two things. The first one happened quite a while ago when we took spectra of some stars at the center of our own Milky Way. And there was no doubt that we were seeing young stars there, which again kind of upended some theories because it was thought, the center of the galaxy is old and dead and blah, blah, blah. No, it's formed stars within the last few 10 million years or so. And then once we've gotten into this Jades era, obviously one is stunned by redshift records and all that. But I have to say, when Joris distributed the startings of the paper with the Lyman alpha absorption, I just was stunned that something like that no one would ever, ever, ever have predicted we would see was there. And that was the galaxy we found in Jades, and Joris, analyzed the spectrum, and Irene helped him figure out how much carbon there was and so on. And I couldn't believe, pardon me, that we were finding that kind of chemical signature now.
Thank you.
Yes, in the back.
Thank you. I have a question about the galaxy with the carbon absorption. And can we estimate how much dust in this galaxy? It's possible?
Yeah, I think it is possible. And Joris Wittstock is here at this meeting, and he can explain how he and Irene did that more clearly than I can.
And one in the back. Yes, you have the mic.
Marcia, thanks for the wonderful talk. As an astronomy journalist, I've been following this field for a couple of decades. And ever since the early 21st century, astronomers have told me we are seeing galaxies so numerous, so massive, so early in the universe, our theories cannot explain them. And then the record was broken again. And now we're seeing galaxies at a redshift of 13.9 showing carbon absorption, apparently. I am wondering, what do you need to observe to really realize there's something wrong with our cherished ideas about early universe and galaxy formation? What else can we expect?
I don't know for sure what else we can expect, because if I knew what to expect, I might go off and try to figure it out. But we still have a lot of underanalyzed data, so there is that point. And this morning, if you were at the IAU symposium talk that Laura Pentorici gave, there's quite a bit more to learn about reionization and so on. But I think what we really are likely to need are more spectra, and in particular, the fact that we've now realized that MIRI can push out the limits to which we can see our sort of well-understood emission lines and things like the Balmer break. We'll be able to go to yet higher redshift, and we're going to get, we may eventually reach a wall that because of faintness, we can't go any further. But I think there's a lot of stuff waiting to be done there to give us more clues about how the stellar population is coming together at these times, because we really have just had a few glimpses so far. I mean, the number of really, really high redshift spectra is still not large. And I think given the mission's going to last for 20 years, and we can therefore take some more really long spectroscopic exposures and take some with MIRI, we're going to figure, we will be pushing ourselves into a corner, I think, if we don't figure it out.
Marcia, the astronomical community owes you a debt of gratitude for your pioneering efforts, along with George, along with so many of you in the audience who are working on this. So congratulations again. Many, many thanks. And thanks to the Gruber Foundation for recognizing this excellence. And with that, we conclude this ceremony. Thanks for being here. Thank you.